We designed a solar generator for a sensor module using our solar dimensioning tool. So far the theory, but how does it perform in reality? Let's briefly recap the simulation results. We found out that the 44 cm square solar panel would be too small to overcome the winter. However, two of the small panels would do the job. Now we are setting up an experiment. We are using two sensors with LoRa modules. The first one is indoors and it is regularly charged with USB chargers. The second sensor is outdoors and works completely autonomously with the solar panel. Over a period of more than 50 days, this will give us plenty of data that we can evaluate. On our server, we are recording not only temperature, humidity and pressure. There is also interesting technical information like battery voltage or LoRa RSSI. We will come back to the server in a later episode where we explain the coding and the functionalities. Since we are starting only in April with our measurements, we use only half the size of the solar panel because we know that in April the so-called solar yield is about double in comparison to the critical winter season. With that, we better can find out where the limits are. During the 50 days period, we will try out different positions of our solar panel on the balcony. We use different places that have different maximum sun visibility, reaching from 20% to 72%. Why are we doing this? We want to understand where the limits are for a stable energy supply. Now let's jump to our experimental results, which are all recorded on a spreadsheet, which you can also download, as always, in the download section. Our spreadsheet is showing now recordings from a test starting on the 5th of April, ending on the 29th of May. It was carried out in Stuttgart, which is located in the southwest of Germany. A spreadsheet is very helpful here because first, it is a lot of data. Second, we recorded not only the voltage states of the batteries and the timestamps, but also the visible sun hours of the different sites and the corresponding weather situation during the whole time period. Third, and this is important, we also calculated benchmarks and forecasts to better judge about the situation. Now, here we are in the top section of our spreadsheet. We are using a TTGO EP03 LoRa board with a BME 280 sensor. From the battery, we can only use about 2000 mAh instead of 3000. This is due to an effect that we are not understanding fully yet. We come back to that in a later episode. From the nominal values that we inserted in the top section here, we calculate already a theoretical runtime that we have an idea what can be expected here, and also things like average voltage loss per day and also the voltage loss per milliampere hour. This is a very simplified calculation. However, the values are helping us to understand where we are during our long measurements. Then, just for information, we have here the informations for the sites and the parameters of our whole arrangement. Next, we are coming to our actually recorded data. In the left two columns, we have our weather information. Of course, the interesting value here is the hours of sun per day, which is 3 here in the first row. The other interesting value here is the sun visibility per site. This is really dependent on where we put the solar panel. Then we have a date and time stamp and the number of our measurement. Next, we look at the voltage states of our sensor number 1 and the sensor number 2. Then we look at the differences that we have from day to day for both of the sensors. Then we have a few comments here explaining changes in the setup or explaining whether a sensor was charged or not. The last two columns on the right side are giving us a really helpful information. They are giving us a runtime forecast for the current situation. It is a sophisticated calculation that is based on the state of charge of the battery and the charging currents. As we can see, the values can be anything between 0 and infinity. In my mind, graphical representations are always great to judge about data of this kind. We have the whole 50 days time period here. The light blue bars are indicating the hours of visible sun at each site. And the yellow bars here indicate the actual sun hours per day. The dashed blue line is indicating the battery voltage of our reference battery 1, which is with the indoor sensor. It is discharging over a few days and is then regularly recharged with a USB charger. The yellow solid line is now the result for which we are doing the whole effort here. We started fully charged and then, despite the cloudy weather and the non-optimal site, it still managed to keep the voltage on a decent level. From day 13 on, we moved to the weakest side, and surprisingly, we still managed with good weather to stay on a decent voltage level. However, when the sky started to get cloudy again, the voltage went a bit down here. From day 33 on, we decided to go to the best side. And despite of the mixed weather conditions here, we experienced that it was able to fully recharge here. Now we are going back to a worst case scenario, which is the site 3. It has the least sun. We were wondering how this looks like on an hourly basis during the whole day. We look at the battery voltage and we look at the current flow. The visibility of the sun is only 2 hours per day, while the current flows during the night and during the sunshine was as expected. It turned out that the solar generator can also benefit a bit from diffuse light. The charging currents is about 10 milliamperes, which means together with the consumption we have about 5 milliamperes positive charging current flow. The diffuse light appeared mainly in the morning hours, while in the afternoon the sun was completely around the house and it was not possible to derive any charge from it. Cool! This is really a positive surprise because it improves the situation overall, maybe by at least 10% in comparison to our simulation. For the ones that are not completely confused now, I want to show a little secret of this spreadsheet. There is some hidden columns where the state of charge calculation is done. This is a pretty sophisticated calculation because the characteristics of a battery is non-linear. So the state of charge calculation of the battery is a pretty complicated formula that you can now see at the top of the Excel line here. But don't worry, there will be a later episode where we explain this behavior and you will get a proper tool for it. If you want, you can reuse this formula at the top here for your own code to calculate the state of charge of a battery. Now, what's the learning of this episode? We saw interesting recordings on the behavior of a solar power generator in the real world. We had interesting insights from the data over 24 hours during the day and over a period of more than 50 days. The performance is slightly better than expected. Diffuse light plays a role here. Looking at the good results in April with half the panel size, we should be okay for the winter with 88 centimeters square for the given consumption. Additional reports will follow after the coming winter. And a state of charge calculator will follow in one of the next episodes. Now, stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.